Welcome to Lecture 23 of Electrical Engineering 525. In this lecture, we will talk a little bit about the design of log periodic dipole arrays. This material is covered in section 7.8 of your textbook. While I think it would benefit you to read all of chapter 7, it's only for the sake of this lecture, it's only necessary for you to cover section 7.8. You might also find it worthwhile to read the Wikipedia article on log periodic dipole arrays. So let's jump right into an example of how to do the design for a log periodic dipole array. In your text, if you look at example 7-3 on page 259, there you will find one example of the design of a log periodic dipole array. And now in class, we will do another, and then for your daily test, you will do still a third design. So for today's lecture, we have the following, which is based on problem 7.8-2 in your text. It says a log periodic dipole array is to be designed to cover the frequency range 84 to 200 megahertz and have a 7.5 dB gain. Give the required element lengths and spacings for optimal design. So the first thing you need to do in these problems is to look at the given gain, which in this case is 7.5 dB, and then look at figure 7-41. which is on page 258 in your textbook. Now, from that figure and from the given gain, you can read off the two parameters that you need, which are sigma and tau. And in this case, for a gain of 7.5 dB, if you look at the 7.5 dB curve in figure 7-41, and then go over to the vertical axis to find sigma and the horizontal axis to find tau, I think you will find that sigma is very close to 0.157 and tau is very close to 0.865. Now, once you have those two figures, to be honest, you are almost halfway home. The next thing you need to do, one of the few remaining things you really need to do, is to find L1, which is going to be the length of the longest element in the log periodic dipole array, and that should be equal to or very close to lambda over 2, calculated at the lowest frequency, operational frequency. Now in this case, we want the log periodic dipole array to operate from 84 to 200 megahertz. So the lowest frequency is 84 megahertz. Now if you calculate then lambda at this lowest frequency, which I will call lambda sub L, is equal to 3.57 meters. And as I said, we want L1 to be about half of that wavelength. So we will set L1 to be equal to, this should be lambda L there, lambda L over 2, which is 1.79 meters. So that gives us L1. L1 is 1.79 meters. Now, the next thing we need to do is to calculate Ln. Now at this point, we don't know what n should be, but we will say that Ln should be close to lambda over 2 at the highest frequency. Now again, returning to the description of the problem, the highest frequency at which we want to operate is 200 megahertz, And so if we calculate the wavelength at that upper frequency, which we'll call lambda sub u, then that's c divided by 200 times 10 to the 6 hertz, which would give us 1.5 meters. And since we want Ln to be about half of that, then we get Ln is close to 1.5 meters divided by 2, or 0.75 meters. And now, to find all the other lengths, what we need to do is start at L1, which you will recall is 1.79 meters, and repeatedly use the equation 7-83, which says that tau is equal to Ln plus 1 over Ln, until we obtain a length that is less than Ln, which was 0.75 meters. So if you do this, remember again, L1 is 1.79 meters, and again, equation 7-83 tells us that Ln plus 1, and so if we let n equals 1, that becomes L2 over L1 is tau, or in other words, L2 is L1 tau. So L2 is L1 times tau, L1 is 1.79 meters, so 1.79 meters times tau is 1.54 meters. And L3 will be L2 times tau, which would give you 1.34 meters. L4 would be L3 times tau, which would give you 1.16 meters. And you just repeatedly multiply by tau, which again, remember, tau is equal to, up here at the top, tau is equal to 0.865. So you just repeatedly multiply by 0.865 until you obtain a length that is less than Ln, that approximate value for Ln that you found above, which was, remember, we said Ln is close to 0.75 meters. So if we repeatedly multiply by 0.865, which again was the value of tau, you see up there, if we repeatedly multiply by that number, we will find that L7 is 0.748 meters. So that is the first time that we will achieve a value that is less than 0.75 meters. So that will be our stopping point. We will take that to be our final L. And furthermore then, since there were 7 values of L, we conclude that there are 7 antennas in the log periodic dipole array. And then the final thing we can do is to calculate the distances between these elements. D1 is the distance between L1 and L2. D2 is the distance between L2 and L3, etc. And so we can calculate up to D6. And the way that we calculate these distances is we find D1 by using equation 7-77, which is sigma equals d sub n over 2ln. So and then after that, we repeatedly use 783, equation 783, in the form tau equals dn plus 1 over dn to find all the other values. So again, we're going to have to use one equation to find d1, and then use the same equation that we used in the above procedure to find all the L's to find all the subsequent T's. So again, according to equation 7-77, D1 is equal to sigma times 2L1. So D1 is equal to sigma times 2L1. For sigma, we found 0.157. Multiply that by 2L1, and we get 0.562 meters. And then for all of the subsequent values of D2, we use equation 783, but instead of the previous form in which we used 783, which was tau equals Ln plus 1 over Ln, now we will use 783 in the form tau equals dn plus 1 over dn. But it's a very similar procedure. So D 2 will be equal to tau times d1, d3 will be tau times d2, and etc. Each time just multiply by tau, which again is 0.865. So we get d2 is 0.486 meters, and d3 is 0.421 meters, and so on down to d6. Again, we stop at d6 because d6 is the distance between element 6 and element 7, and there are no more elements after element 7. And so this is the procedure for calculating the, for designing a log periodic dipole array. And you can, as I say, again, you can see another example of this in your book, in example 7-3, which is on page 259, and you can also read in section 7.8 for more details of how the log periodic dipole array works, which actually is interesting. So be sure to take a look at that, and or the Wikipedia article on log periodic dipole arrays. So finally now, the final thing to discuss is the problem for test 23, and this is just a modification of problem 7.8-4. And in the actual problem 7.8-4, they discuss the addition of extra elements on the end of an array, and we won't cover that. This is a slightly more advanced topic. Now, there's certainly no big deal to it, but it's a little more advanced. So we'll just stick with another example, though, that is exactly like example 7-3, or like the example that we have just worked. So in this problem, we have the following. Again, this is a modified version of problem 7.8-4. We want to design an optimum LPDA, that's log periodic dipole array, to operate from 470 megahertz to 890 megahertz with 9 dB gain. And so problem 1 says what is L3 in meters, 2 says what is the number of antennas in the array, and then there will be a third problem on test 23 in class. So that concludes lecture 23, and good luck.